Thank you, Liz, and thank you to the HMNH for sponsoring this wonderful series. Evolution really does matter, and I think on behalf of the whole Harvard community, we'd like to thank the HMNH for sponsoring this fantastic series. So thanks. So today I have really two goals. The first goal is to talk a little bit about what we know about what happened in human evolution since Darwin published The Origin 150 years ago. I think Darwin would be really surprised and pleased, maybe a little horrified at what we've discovered in the last 150 years. But I also want to talk about some larger problems that result from that evolutionary history. I think that one of the things that science does very well now is focus in on small problems. We're very good at reducing problems to their very simple elements and studying genes and cytokines and transcription factors. But Darwin had never heard of any of those terms. He didn't know how genes worked. He didn't know about how cells interacted. Yet he was able, his genius was to look at the big picture and to think about the grand, the large, the ultimate processes that drove large-scale change in evolution. And I think that sometimes as science progresses, we have this tendency to continue to focus our microscopes down and down at the smaller level, and sometimes we forget those kind of big questions that are very important and which today I hope to show you are very relevant to thinking about how we treat or how we combat some of the huge problems that we face in our generation and the coming generations. Let's see if this is going to work here. It's not working. Whoops. Let's see if I can get my little slide thing to work here.
Maybe not the smartest.
Hey, it's a Mac, not a PC. There we go. All right. So, as evolution, as you, I hope, well know, is change over time. And this is Darwin's famous figure, the only figure from The Origin of Species, which shows that as some species over time don't change very much, most go extinct, but there's many branch points that can occur in other species that over long periods of time can lead to novel forms, descent with modification. Now, the idea that evolution occurs was not actually that controversial in Darwin's time. People had been writing about and thinking about change over time for quite some time. Lamarck had written about it. Darwin's grandfather had written about it. But the idea of natural selection as the agent of change over time was extremely controversial. And perhaps it was no more controversial than when applied to human evolution. Because if you accept that evolution occurs, it raises a number of really important questions about the evolution of our own species. And the three most common questions, of course, are what happened in human evolution? Are humans still evolving? And what's going to happen in human evolution? Well, as scientists, we're probably better at answering the first and the second questions than the third question. After all, evolutionary biology is really a historical science. We're good at looking backwards and trying to explain what. And when we do make predictions, we tend to make predictions actually about the past. So we can make predictions that we're going to find certain fossil species. But we're not really in the job of making predictions about the future. But as I'll argue today, we're in an interesting period in our evolutionary history because of culture. Culture has such profound effects on our biology that the interactions between biology and culture, I think, do enable us to make some predictions about the nature of those interactions and also to help us think about how we can use those interactions to solve some of the problems that we face. So what I'd like to do in the next hour is first address a little bit about what we think happened in human evolution. I'm going to focus on three events. Now, there's a lot of information about human evolution, and people like me can spend their entire lives studying little fossils and little events and sites, and scientists and scholars love to obfuscate things and make things seem as complicated as possible so that people value us more. But actually, I would argue that you can stand back, and when you look at all the complication, you can see that there are a few really major events that occurred. And I would say that they're the divergence of our lineage from the ape lineage, the origins of the genus Homo, our own genus, and the origins of our own species, Homo sapiens. And then one incredibly important cultural event, the origins of agriculture, whose effects are still resonating today. I'll then talk a little bit about what happening now in human evolution, although Pardis Sabeti covered that far better than I could possibly cover last week. And then I'd like to talk a little bit about our evolutionary future. So a simple reminder of how evolution works. Populations have variation. All of you look different from each other, which is, I think, a good thing. And much of that variation is heritable. And over time, you can get changes in the variations in populations through a variety of processes. So one could be simple chance. So a bunch of us could get on a boat and go to a new island. And if we sample a subset of the variation in the population here, there'll be a new distribution of genes in that population. And evolution will operate on that different genetic background than the initial genetic background. So these are events that occur by chance. The other way that evolution can occur is through a filter, and that's really what natural selection is. That some of these variants confer advantages or disadvantages in terms of reproductive success. So when there's competition and environmental change, natural selection can act as a kind of sieve or a filter, such that some genetic variants are more likely to pass through to the next generation, and over long periods of time, that can cause huge amounts of change. So it's really an agentless process, and I think that that's one of the reasons that Darwin avoided the topic of human evolution in The Origin of Species. He actually gave it really only one line, in which he said this famous line, wonderful use of the passive, "Light will be thrown on the origin of man and his history." Now, there are several reasons Darwin avoided it in The Origin. The first was it was pretty darn controversial. And I think the most controversial aspect of the theory of natural selection is that there's no agent. It just happens. You have a number of ingredients, and evolution just occurs as an outcome, an epiphenomenon of those processes. And so, in fact, I think that's what really bothers proponents of intelligent design. They really want to see some agent out there, be it God or some great creature in outer space, causing change to occur. The other thing, of course, about evolution of humans that really makes people uncomfortable is the idea that we're most closely related to apes, or some people think monkeys. And this is actually a cartoon from Darwin's time. It just showed how deep-seated that concern is. Yet, of course, humans are no different from other creatures. The same kinds of biological processes operate in us as in other creatures. And Darwin, of course, knew this. And in 1871, he published his magnificent volume, The Descent of Man, in which he made some speculations about human evolution. Quite remarkable for the time, since there was almost no evidence about what happened in human evolution. But Darwin reasoned, of course, that the ingredients for evolution in humans are no different from other creatures. After all, we have heritable variation. So in this famous Harvard graduate, you can see his family. Everyone's a little bit different. There's competition and differential reproductive success. And most of the time we don't see it. But of course, during pandemics or other sorts of events, that of course becomes much more obvious to us. And of course, there are chance events that affect how genotypes move around the globe. For example, population migrations. Most of us in this room, I dare say our ancestors did not live here a few generations ago. That's certainly the case for me. So we've also got all kinds of chance events that occur. So what did happen in human evolution? I just love this stuff. Okay. Now, again, in 1871, Darwin didn't really have much information, but he did infer correctly that we're more similar to African apes, that we probably evolved from those African apes. But he didn't really have any of the details about what happened between the apes and between humans. He made some very interesting and educated guesses, which should be the subject of another lecture. But since then, 150 years later, we've really thrown a lot of light on this problem. And I think Darwin would be totally excited by what we now know. And again, as I said, as you step back from all the problems, we know that there are three really major events that you can distill out of all the complexity that we see. And that is the divergence of the hominin lineage from the apes, the origins of our own genus, the genus Homo, and the origins of Homo sapiens. So let's talk about that first big event, the divergence of our lineage from the ape lineage. And to borrow a phrase from Spencer, this might be argued to be about the survival of the less costly and the less picky. So let's see how that works. So it used to be thought for many years that humans are more closely, that chimps and gorillas are more closely related to each other than either are to humans. And that is obvious because chimps and gorillas are actually very similar. If you take a bicycle pump to a chimp, basically, and blow it up, you get a gorilla. A gorilla is basically a blown-up chimpanzee, and they knuckle walk, and they're morphologically similar in all kinds of ways that mostly can be explained by size. But we now know from genetic evidence that chimpanzees and humans are actually more closely related to each other than either of us are to gorillas. That's a really exciting fact, because it means that unless all the similarities between chimps and gorillas evolved independently, it means that the last common ancestor of gorillas and the chimp-human lineage, plus the last common ancestor of the chimp and human lineage, must have been very much like a chimpanzee or a gorilla, which amounts essentially to the same thing. We also know from genetic evidence that that last common ancestor was about 6 to 8 million years ago. And because it was mostly chimp-like, we know it lived in a forest, it probably ate a lot of fruit, and it probably was a knuckle walker. But that's all we really knew. And until a few years ago, the fossil record for human evolution really went back to the genus Australopithecus, so only about 3 million years ago. And so we were missing the first 3 million years of human evolution since our divergence from the last common ancestor. And over the last decade or so, it's been an incredibly exciting time to be in my field because we've gotten a number of incredibly exciting fossils which tell us what these very early hominins were like. It's just a glimpse at this point, but it's a pretty good glimpse. And the main cast of character are these 3 critters. These are 3, at the moment, they're divided into 3 genera, so 3 different genuses. There's the genus Sahelanthropus from Chad, discovered by Michel Brunet in the Sahara. This is about 7 million years old, and this is the most famous skull. This is a skull of the hominid. It's been nicknamed Tumai. That's a nickname. Another species from Kenya that is about 6 million years old, called Auroran, just a bunch of fragmentary bits, but there's this wonderful femur and a few teeth. And a variety of material from Ethiopia called Ardipithecus. There are actually 2 species assigned to this now, and they're about 6 to 4.5 million years old, and lots of fragmentary little bits. The interesting thing about all these fossils, and I'm going to focus on Tumai, Sahelanthropus, because it's the best represented. It's a nearly complete skull, and I had the privilege also of working on reconstructing and analyzing the skull. And here I'm comparing this skull in the frontal view and in lateral view with a chimpanzee. And I don't think you have to have a PhD to figure out that this looks a lot like a chimpanzee, right? It's actually very chimpanzee-like, except for a few features. One of them is that its canines are a little bit smaller than in the chimpanzee, and its cheek teeth, I'll show you another picture in a little bit second, are a bit larger and a little bit thicker. And even more exciting to me is that its foramen magnum, the hole through which its brain, its spinal cord sticks out, points downwards rather than backwards. And since your neck has to articulate with the foramen magnum more or less perpendicularly so you don't shear your neck off your head, that means that when Tumai was walking around looking where it was going, its neck was pointing downwards, which means it must have been a biped. So we know that the earliest hominids were basically chimp-like, but they were bipeds, and they had slightly bigger, thicker cheek teeth and slightly smaller canines. Other than that, they looked pretty chimp-like. Now, why did this occur? Well, this is a kind of a thermometer, a graph, over the last 70 million years. It's a graph of the temperature of the ocean. It comes from benthic foraminifera, and they have little carbonate shells, and the oxygen in those shells, there are different ratios of oxygen isotopes, which tell us the temperature of the water when the little critter made its little shell. And then they drop down to the bottom of the ocean, and we can drill them out and measure the oxygen. And it shows us that just at the end of the Miocene, which is the period from about 25 to 5 million years ago, just at the end of the Miocene, there was a dramatic and rapid cooling of the Earth. It was an incredible change in climate. And what happened in Africa during that time period was that much of Africa prior to then was covered with rainforest. But during that cooling, the woodland zones expanded and the forest started shrinking. So imagine you're a chimp-like creature at the edge of a forest, and there's this rapid shift going on, and all of a sudden, the forest around you is gone. Well, you can either go extinct, or you can adapt. Adaptation can occur. I don't want to argue this is be teleological here. But I think that the changes that we see make a lot of sense, because chimpanzees are knuckle walkers and tree climbers. They're really good at climbing in trees, but they also can walk terrestrially. But that strange combination of adaptations makes them really lousy locomotors, right? A chimpanzee, some former graduate students of mine actually managed to put masks on chimpanzees and get them on a treadmill. They did not do it here at Harvard, thank God. And they were able to show that chimpanzees, when they locomote, actually use 4 times as much energy as a human, because chimpanzees are very costly at locomoting. So imagine the forests are shrinking, and the fruit resources that you're interested in are further apart. The ability to locomote in a way as a biped that uses much less energy than as a quadruped, saving 75% less energy, could really make a difference in terms of your fitness. In addition, if the forests are shrinking and you're not living in a nice rich forest with lots of fruit all the time, and chimpanzees really do love fruit. What you think is absolutely true, but imagine the fruit's not there all the time, and you have to fall back on foods that aren't as as succulent and juicy and soft as fruit, it would be really useful if you had teeth that were thicker and larger to help you break down those more mechanically demanding foods. So hominids that were able to save energy locomoting and also chew foods that were less preferred but necessary to survive during seasons when fruit weren't available probably had more offspring, leading to the origins of the hominin lineage. So clearly it was successful because we know that after the origins of those first hominids, we get a radiation of Australopithecines. So the Australopithecines are a class of hominids. They're very confusing. There are lots of them. There are about 6 to 10 of these species. And they live from about 4.5 million years ago to a little under 1 million years ago. And the most famous of the Australopithecines is Lucy, a partial skeleton who's constantly coming up in the news for various reasons, some of them controversial. Anyway, Lucy was an Australopithecus afarensis who lived about 3 to 4 million years ago, which is a good representative. But Lucy's one of just a group of Australopithecines, and they're all variations on the same theme. They all have pretty much small brains, a little bit bigger than a chimpanzee, but not really much bigger than a chimpanzee. They were bipeds. They had snouts. They loved to eat fruit, but they probably ate other things as well. We know that they walked around as bipeds, but we also know they had lots of features that enabled them to be really good at climbing in trees. And for millions of years, the Australopiths were it in terms of human evolution. And we might be sitting in Africa in a tree in the evening now, hoping a saber-toothed tiger doesn't eat us. And as Australopiths, if it hadn't been for the next really big event in human evolution, which occurred around between 2 and 3 million years ago, and that's the origins of our own genus, the genus Homo. And maybe this really might be about the survival of the fleeter and the smarter. So again, climate rears its ugly head. Climate change is incredibly important in human evolution. And here's another graph blown up of that previous curve, and I'm afraid I've reversed the axis, so it's now colder on the right. But you can see that there's lots of fluctuations in the Earth temperature, but starting between about 3 and 2 million years ago, the Earth got colder again, yet again. And during that time period, we know that in Africa, a lot of those woodlands I was showing you, particularly in East Africa, gave rise to more open grassland habitats, the savannas. So this is sort of the crisis of the late Pliocene. Now imagine you're a hominid living there. There's a number of interesting evolutionary solutions that could occur in order to solve that crisis, and we see 2 of them. One of them was the evolution of a group of Australopithecines we call the robust Australopiths. And these were basically low-quality food specialists. And they show up around 2.5 million years ago, and they survived for quite a while. But the other was our genus, the genus Homo, which showed up at the same time. But we were the high-quality food specialists, and that has had resounding effects that last to this day. So let's first just mention the robust Australopiths. Not that they're not interesting, but basically if the chimpanzees were if the Australopiths were sort of chimps on legs, these are sort of like cows on legs. They have enormous teeth. You see the size of these teeth? That's a chimp's palate. Here's a Australopithecus boisei palate. Their teeth are 3 times the size of a chimp's teeth or your teeth. I mean, they're enormous. This is why Louis Leakey called this Nutcracker Man. They had enormous faces. The muscle here, the temporalis muscle on the side of the head here, which in humans is a very small little slip of a muscle, in one of these must have been like a great big porterhouse steak. It would have been enormous. But otherwise, they had small bodies. Their brains were just a little bit bigger than chimpanzees. They were probably good at walking, but they probably were also good at climbing trees. They're one solution. They went the cow route, but we went the carnivore route. We went a totally different route. And we became adapted, our ancestors that is, became adapted for a high-quality, energy-rich diet. And we see initially with Homo habilis, which is a very obscure species, but certainly by the time we get this species here, Homo erectus, creatures that have bigger brains, much more modern, bigger bodies, smaller teeth, very much like our teeth. They lost the snout that is true in chimps and Australopiths. So we have vertical faces. We got our big, beautiful external schnozzes. And we became very good at not only at walking, but also endurance running. What we're really about here is the origins of the first hunter-gatherers. These were creatures that gathered foods, but we also know from the archaeological record that they were also killing animals and eating meat. And they had simple stone tools, and they probably processed their food. And I believe that one of the ways in which we became hunters was by becoming really good at running. So this is a little movie of a bushman who practicing something called persistence hunting. In persistence hunting, we take advantage of the fact that humans, because of our long and springy legs and all kinds of other features in our body, are really good at running in hot weather. We can cool down because we can sweat, we don't have fur, and we can cool down while running at speeds that forces animals to gallop. And when when a quadruped has to gallop, it cannot pant. And when it cannot pant in the heat, it generates lots of heat, and it overheats, and it dies. So this hunter-gatherer here is chasing an animal in the middle of the day. It takes him about 10 to 15 kilometers of running. And what he does is he drives that animal into hyperthermia, and he can kill it without any real technology. And that's important because projectile weapons, a spear point, wasn't invented until 200,000 to 300,000 years ago. The bow and arrow was invented probably less than 100,000 years ago. Hunting dogs were domesticated only 12,000 years ago. So for most of human evolutionary history, the only weapons that we had to become carnivores was basically a club or a sharpened wooden stick. And I don't think any of us would want to run up to a kudu and just poke it with a stick. So the key point about this, and I don't want to give a lecture on running, I want to give a lecture really about energetics, is that this new kind of life, this new body, enabled Homo erectus and its ancestors and its descendants to have a very energetically intense and complex kind of life. So if we compare what we think we know about Australopithecines and Homo in terms of energetics and life history, we can calculate that a typical Australopithecine, particularly a mother who's lactating — you need a lot more energy when you're lactating than when just normal life — would have needed about 1,000 to 1,600 kilocalories per day. But a Homo erectus mother would have needed 2,500 kilocalories a day. We can guess that the interbirth intervals for Australopithecines were much like chimpanzees, about 5 years. But there's good reason to believe that the interbirth interval of Homo erectus was pushed down to about 3 years. We know that the Australopiths were eating fruits and seeds and nuts and tubers, but Homo added meat. And of course, that's not an easy thing to do. And that involved an expansion of day ranges. We know that the genus Homo was making stone tools. We know that they were processing their food. And there's good reason to speculate that mate provisioning, sharing food in a central camp, became very important in this kind of way of life. I'd love to talk about that, but that's really another lecture. Brains are particularly important in all of this. So this is a graph of brain size, the volume of the brain over time. That's Tumai there, with a shrimpy little chimp-sized brain. We're missing this huge fossil record here. And these are the Australopiths. They have pretty small brains, just a little bit bigger than chimpanzees. But as soon as we get to the genus Homo, we get this expansion of brain size. A little bit at first, but then it clearly accelerated. And by 1 million years ago, brains started going ever faster towards modern sizes. So we had this release of constraint on growing a big brain. And that's very important. And I'll explain why and how energetically that's related to many of the issues that we face today. So the descendants of Homo erectus did very well. They flourished. They left Africa. We see them in the Caucasus in Georgia by 1.8 million years ago. They get into Asia, both South Asia and East Asia, by 1.6 million years ago. They certainly got into Europe by at least 1.2 million years ago. I'll bet that we'll find fossils in Europe that are even older than that. And they continued to evolve. And their descendants turned into species that many of us are familiar with, such as the Neanderthals, who lived in Europe, or Homo heidelbergensis, which lived in Africa and were the ancestors of Neanderthals. And in Asia, Homo erectus continued to evolve and change. And of course, there's that wonderful example on that tiny little island in Indonesia, Homo floresiensis, Homo erectus, which actually shrank down to become a very small creature. And along with these changes, we get also technological changes, such as the invention of cooking, a very important change in our evolutionary history, which my colleague Richard Wrangham has been doing a lot of work on. We get the evolution of projectile technology, again, starting around 200,000 or 300,000 years ago. And we would all be living like that, basically with spears and big brains, but leading sort of very hunter-gathery lives, if it hadn't been for the third major event in our evolutionary history, the origins of our own species, which might be about survival of the even smarter. But notice the question mark there. OK, so we know that our species evolved in Africa, and we have abundant genetic evidence, and we have abundant fossil evidence for this. So the genetic evidence is that all humans are very closely related to each other, and we share a last common ancestor that lived in Africa between about 100 and 200,000 years ago. We also have Neanderthal DNA, and it shows us that the last common ancestor of humans and Neanderthals probably lived about 300,000 to 500,000 years ago. We also have a rich fossil record in Africa, showing us early modern humans, people with brains and heads and skulls very much like yours and mine, that lived, for example, and here's so far the leader of the pack, from Homo in Ethiopia, a beautiful skull that's about 190,000 years ago. This is the oldest bona fide Homo sapiens, but there's some others as well from Africa, and there's some others that are obscurely dated who might push the date back even a little bit further. So we know that humans evolved in Africa. More interesting thing about the origins of Homo sapiens is that we're actually not very different from our close relatives. So we probably evolved from Homo heidelbergensis. This is a famous skull from Africa called Kabwe, or Broken Hill. Probably a likely ancestor of this skull. This is actually the old man of Cro-Magnon. I just picked him because it's sort of fun. And he's very representative of early humans. And really the big difference between the human and the Homo heidelbergensis is not brain size. Actually, brain size is actually about equivalent in humans and, say, Neanderthals. It's actually the shape of the skull. So humans have a very round or globular brain case, which may be caused by some changes in some of the structures of the brain. And our faces are very small and tucked in underneath our brain case, right? So you can see this as an enormous, big, huge, tall face that projects forward from the brain case, whereas our face has been shrunk down and retracted underneath the brain case. And the end result is a much rounder skull with a steep forehead, a rounded occipital. We lost those great big huge whopping brow ridges. Our orbits got small. We have a little groove along the side of our nose. And people like me love to find lots of little anatomical details which we can discuss ad infinitum and make everybody's eyes roll into their heads. But I won't do that. What I will do is point out that some of those features might actually be very significant in terms of adaptation. There are not many, but there are a few that might be. And one of them is actually work that we did in my lab, is that the size of the middle cranial fossa, which cradles the temporal lobe, is relatively larger in humans than it is in other species of hominids. And that suggests that maybe we had bigger temporal lobes. And of course, the temporal lobe is very important as a part of the brain that's involved in language and in memory. It's also involved in spiritual thoughts, so maybe believing in God is an outcome of having big temporal lobes. We also have, because of our retracted faces, we have shorter oral cavities. And an important aspect of speech is that the ratio of the length of the oral cavity to the height of the vocal tract here has some effects on the clarity of sounds that we can produce, particularly vowel sounds. And so this shift in anatomy may have made us speak a little bit more clearly, which could be an advantage. I don't know. So humans, once we evolved, whatever our advantages were, we see changes. So we started to invent all kinds of new tools and technologies. When we look in the fossil record of Africa, starting around 200,000 years ago, we see all kinds of innovations, such as invention of new kinds of technologies, such as bone points and harpoons and little microlithic tools. And they're now catching fish, and they start making art and all kinds of blade tools. And so you begin to see this creative explosion that's accelerated ever since the origin of our species. We also begin to move out of Africa. We first hit the Middle East around 100,000 years ago, and humans move into Europe around 40,000 years ago. We move into Asia maybe around 60,000 years ago or so, and into Australia perhaps by about 40,000 years ago. And wherever we go, that's it for everybody else. So the Neanderthals in Europe disappear within 10,000 years of modern humans arriving in Europe. Homo erectus disappears in Asia when modern humans arrive there too. So we colonize the whole world. So thanks to a series of chance events, we became really energetically intense hunter-gatherers. We became omnivores with meat, a very important component of our diet. And so we now love foods that are rich in energy, such as fat and protein and carbohydrates. Which is like, what is it that George Bush I used to always eat on a campaign? It was pork rinds, right? That's a classic human food, right? Particularly if you're trying to get votes in Texas. We also became highly mobile endurance athletes, capable of incredible activity in the heat. So if it's a warm day for the Boston Marathon, people will be fine. They may have to drink a little bit more water, but woe betide anybody who brings their dog on a run in the marathon. The dog will die. We can walk or run huge amounts of in the day and do it regularly. We became very smart and inventive, invented language and culture and all kinds of tools. And of course, we became obligate cookers. And as my colleague Richard Wrangham has argued, humans actually now rely on cooking to survive, and enabled us to get more energy and a wider range of food. And last but not least, we became very good breeders. We can pump out, as hunter-gatherers, babies every 3 years. And that's a very important point. I want to show this to you in this slide. So this is a graph of the life history of chimpanzees and hunter-gatherers. And we're about the same, right, in terms of gestation. Chimps have an 8-month gestation. We have a 9-month gestation. But thereafter, our life history is stretched out, right? A chimp grows its brain in about 3 years, but we take about 6 years. A chimp reaches adult size in about 12 years and has its first baby about 14 years. It takes us about 18 years to reach adult size and have our first babies. And we can shorten our interbirth interval to about 3.5 years, whereas in chimpanzees it's about 5.5 years. And one of the major reasons for that is that we've pushed weaning way up. So we wean our babies at about 3 years, whereas chimpanzees don't wean their babies until about 5.5 years. So a human can have about 5 offspring in her life, whereas a chimpanzee female can have about 3 to 4 offspring. You combine that fertility with low mortality. This compares mortality rates in chimpanzees and hunter-gatherers, and you can see just how successful that hunter-gatherer way of life was. Right? We have lots of babies, and a lot of them survive to become adults. Another especially important interaction here in terms of energy is our brains. This is a graph of the metabolic cost of different tissues in your body. And you can see here that one of the big ones is the brain. You're sitting here listening to me, hopefully relaxed, having a good time, thinking about dinner. And I hope that you're not concentrating too hard. And even if you're not thinking very hard, your brain is still using about 20 to 25% of your body's metabolism at the moment. It's a very thirsty, gas-guzzling tissue, right? And it's very costly not only to maintain, but also to grow. It takes us to grow our brains. As I said before, it takes a chimpanzee about 3 years to grow its much smaller brain.
What is the chart and the graph on the bottom?
I'm sorry?
The scale? Years of age?
Oh, yeah, that's age. That's age. So that's over time. So brain is a relatively more costly tissue in a baby than it is in an adult. Thank you. So in order to pay for that big gas-guzzling engine under the hood, we have to have fat babies. A human baby, well, not this one is a little bit off the charts, obviously, but typical human babies in non-industrial societies are about 15% body fat compared to most primates, where they're about 4% body fat. And by 6 to 7 months, most babies are consuming so much energy that a human female cannot produce enough milk to satisfy that baby's needs. So we have to start supplementing our babies. And we have to supplement them for many years. So fat plays a very important role in having and growing and maintaining big brains. And because we need to have those energy reserves in order to pay for our babies' big brains and allow them to grow, fat is also important in maternal biology. So females, of course, have the ability to put on more fat than males, and probably we have evolved over the time the ability to be pretty good at packing the stuff on, because in bad times, you need those reserves to make it through to when times become good again. So thanks to this energetic strategy that we adopted, this high energy strategy, this gas-guzzling strategy, if I may use the metaphor, hunter-gatherer way of life became very adaptable and very successful, and it obviously stood us in good stead for millions of years. It lasted from at least 2 million years until the extremely recent past. And yes, there were enormous changes that occurred over that time. Technologies improved, brains got bigger, methods of hunting and gathering improved, but more or less these are variations on the same basic hunting-gathering way of life until the next really big event that occurred. But it wasn't a speciation event, it was a cultural event, and it was the origin of farming. And it happened more than once, and in different parts of the world. And its effects are arguably just as important, if not more important, for our life today than what happened before. It's important to remember that farming, as profound as it is also incredibly recent. Just think about it. Our ancestors were hunter-gatherers for at least 100,000 generations in the genus Homo, and in our own species, the Homo sapiens, for about 10,000 generations. But the oldest farmers were really only about 600 generations ago, actually probably a little less in many parts of the world, far less than 600 generations ago. Farming is an incredibly recent invention. But it's a profound one because farmers use energy in a way that's totally different from the way hunter-gatherers use energy. They've got this positive feedback loop in which they produce a lot of food. They can produce a surplus. A lot of that food is easily ground up and turned into porridge and mash and stuff we can give to our babies. We can shorten our interbirth interval. We can have larger populations. And that, of course, drives this feedback loop where we use more land and we produce more technologies and we can produce more food so we can have those short interbirth intervals. And the cycle goes on and on and on and on. And it's a positive feedback loop that drives population growth. And so here's a graph of population growth over the last few million years. here's the origins of agriculture, and it's been an exponential ever since, with, of course, amazing increases occurring with the origins of industrialization. And so we go from millions of years living as hunter-gatherers in small, very ephemeral camps that moved frequently, to the first villages, to the first towns, to now gigantic megalopolises, which, of course, are a far cry from what we originally lived in. Which brings up the question, are humans still evolving? And there's much debate about this. There are some people, such as this fellow, a really interesting professor at the University of Utah named Henry Harpending, who argues that human evolution is now accelerated, that we're actually undergoing greater levels of natural selection than ever before in our evolutionary history. This fellow, professor at London, has argued there's no evolution going on now at all. He's probably wrong, as you probably learned from Pardees Sabeti, who have, I think, sensibly shown, I think, quite a lot of evolution going on. And of course, it makes sense that there's evolution going on. We still have all the ingredients for natural selection. We have heritable variation. We have competition and differential reproductive success. And we have chance events that affect humans. And as Pardees showed last week, we have all kinds of evidence for natural selection. We have evidence for genes that enable adults from populations descended from pastoralists to digest milk when we're adults, rather than which can avoid, not only allow us to drink all kinds of milk, but and avoid embarrassment in some situations. We have genes that, for those of us who don't live in the equator, to decrease the amount of melanin in our skin so that we can pick up more vitamin D in the winter. Genes that protect us against sickle cell anemia in parts of the world where, that give sickle cell celling, that protect us against malaria in some parts of the world, thick hair in Asia, and the list goes on. One set of genes that I think are particularly important are those related to metabolism. Because while hunter-gatherers certainly go through periods of good times and bad times, one could argue that farmers go through far more extreme swings in terms of food, from feast to famine. And there's evidence that over the last few thousand years, there's interactions between genes that interact with the environment that affect insulin resistance and pancreatic cell function, such that the interactions between these genes and various environmental factors has led to an increase in diabetes, and those increases are greater in some populations than others. And they appear to be, for the most part, greater in populations that evolved agriculture more recently. So the Pima Indians, for example, evolved agriculture about 2,000 years ago, and they have among the highest diabetes rates in the world. So this is a graph of the prevalence of diabetes of Pima Indians living in Mexico compared to other Mexicans, and Pima Indians living here in the United States. They have the world's highest rate of diabetes. Really, really terrible healthcare problem there. What about selection occurring right now? Well, certainly there's stabilizing selection. There are mutations that arise that are extremely harmful, and they're rapidly lost to the loss, such as Tay-Sachs disease, for example, which we have this overproduction of fatty acid in brain cells, and it's incurable, although now we have genetic screening, so there are probably going to be an increase in carriers in Tay-Sachs disease. And there are other kinds of mechanisms of cultural buffering that are also operating. So, for example, diabetes, juvenile diabetes, many generations ago, was a very serious disease, probably even a death sentence. But now we have insulin. We can treat kids with diabetes, and of course we can treat adults who get diabetes. And in fact, it's become an extremely profitable part of the healthcare industry. I don't know how many of you are invested in companies that make a lot of money off diabetes. What about other kinds of selection? Well, they're harder to measure, although there are all kinds of ideas out there. There are arguments that people who are more beautiful have more offspring. People who are wealthy have more offspring. These guys certainly did. People who are more symmetrical may have more offspring. Now remember, though, that for natural selection to be occurring, those variants have to have some heritable basis. And I think the jury is very much out. Actually, I think it's very questionable that any of these features really are actually all that heritable. How about evolution by chance? There are still, of course, chance events occurring. There are migrations. My ancestors did not live here a few generations ago. They migrated here. Surely that's happening. But there are some mitigating effects. And one of them is a very interesting one, which is that if you take all the genetic variants in the world, right, all the things that make every person different from another person, it turns out that within any one population, you have about 86% of the total human genetic variants, which is very different from, say, chimpanzees, in which if you compare different chimpanzee populations, each population has only about 28% of the total species variance. So what does this mean? It means that, let's just say the entire world goes to hell in a handbasket, and all that's left is, say, Australia. I just picked Australia because of this movie. that means that we'd still have most of the genetic variants still in this room because of that interesting fact. And that fact, of course, arises from the fact that we all share a recent ancestry from a pretty small population not too long ago. So I'll bet if you took a Cro-Magnon from, say, 30 or 40,000 years ago and put him in Beverly Hills, he'd do just fine. In fact, probably make a lot of money doing Geico commercials because there hasn't been all that much evolutionary change over the last few thousand years. But nonetheless, that change is still occurring, and that change is still important. What does, though, that mean about our evolutionary history? Because, of course, I think the key thing that's changing is the increased amount of cultural buffering that's going on. The fact that we have now tests to screen ourselves as to whether or not we have disease. We have insulin to give ourselves if we get diabetes. We have all kinds of mechanisms to buffer ourselves from these challenges. What does this mean? Well, one possibility is that nothing will happen, right? We're actually going to go on with ever-increasing cultural change, and we'll be exactly the same 300, 500 years as we are now, which would be very useful for Hollywood because that means that you don't have to change, no expensive makeup, pointy ears, etc. for the actors except for those who play Vulcans, right? So. And I think that's a good thing. I mean, how many of you in this room would like to become a hunter-gatherer? I think that child would like to become a hunter-gatherer. But the rest of you, how many of you would like to, I mean, how would you like to give up French cheese and iPods and Harry Potter and sushi and Californian wine and toilets, for that matter? We have lots of wonderful inventions that have made the world a much better place. Among them, we live longer. Now, the worst thing you possibly, this is a graph of probability of death against age. And as you can see, probably the worst thing you could have been in human history was a French farmer in the 16th century. They had rough, tough lives. This is why the revolution happened, after all. Foragers, in terms of their mortality profile, look not too different from Swedes from the 18th century. They do pretty well. And it's only in recent years that we've, because of all these advances, we've increased our lifespan so that we now can expect to live into our 70s and 80s and even beyond. But there are also some very serious and profound downsides, and that is that our bodies are not necessarily all that well designed for the world that we've created. We have all kinds of diseases that would be unknown to hunter-gatherer. Cirrhosis, asthma, diabetes, diverticulitis, flat feet, gout, impacted wisdom teeth, heart disease, and even psychological diseases. I don't know if hunter-gatherers get Weltschmerz, but perhaps they do. One example, which I'm very interested in, because we're working on it in my lab, and I'm kind of obsessed by feet. Everybody in my lab knows that I'm walking around in barefoot all the time in the day, because I'm really interested in the evolution of feet, is flat feet. How many in this room have flat feet? A large number, right? About 25% of Americans have flat feet. If you had grown up not wearing shoes, I guarantee you would not have had flat feet. You get flat feet by wearing shoes with insoles. That makes the arches of the muscles in the arch weak, and then the ligaments eventually collapse, and your foot collapses. If you have strong feet, you don't get flat feet. But what do? We give our people insoles, right? And that cures the problem. Fine, it's not a big deal. So I'm sure that at least a quarter of the room is wearing insoles right now, I mean, orthotics. But some of these problems are far more serious than flat feet. And most of these are the diseases of affluence: obesity, heart disease, type 2 diabetes, osteoporosis, cancer, the list goes on. In my lifetime, since I was born, the percentage of Americans who are obese has doubled in my lifetime. 2/3 of Americans now are either obese or overweight, which is a really frightening statistic. It's a really scary statistic. And of course, obesity is strongly linked to diabetes. Obesity actually is one of the major causes of diabetes. This is from the CDC. I just got this off the web yesterday. This is a graph of adults over the age of 50 diagnosed with diabetes. And you can see the rates are steadily rising, and the CDC predicts that in 10 years, a quarter of adults over the age of 50 will have diabetes. This is really, really scary stuff. We have other scary stuff going on. We live in high population densities in parts of the world in which people are living side by side with animals and chickens. And the pigs get our viruses, and the pigs also get the avian viruses, and they get remixed in that wonderful gut of the pig and come out in forms that could be highly dangerous to us. So we're at increased populations not only cause greater likelihood for epidemics because of the ability for us to interact and spread disease, but also even to breed new diseases. We have greater amounts of social conflict. Now, chimpanzees, despite what you may think, are actually a pretty rough, tough lot. My colleague Richard Wrangham has documented just how much violence occurs in chimpanzees. Males compete with each other a lot. There's actually about a fairly high degree of lethal violence in chimpanzees. But foragers tend to be much less violent. And the reason, I think, is pretty simple. If you're a forager and you don't like somebody, you just move. Right? You're not stuck there. You go to another watering hole or another mongongo tree or another river or whatever and get away from that person, right? But as soon as you become a farmer, you're stuck. You have land, you have property, you have to stay there. And then you get property, right? And you get wealth, and then you want to have your wealth and you want to take somebody else's wealth, and you get increased conflict. And farming and sedentism have caused an increase in social violence. And finally, the most scary problem of all, of course, is global warming. This is the famous Keeling curve of carbon dioxide in the Earth's atmosphere over the last 50 years. And you can see that it's been rising steadily, steadily as we pump carbon dioxide into our atmosphere. And we know that 75% of that curve's rise comes from burning fossil fuel, and another 25% comes from deforestation as we clear land, we clear forests, so that we can farm more of it and use it for other purposes. Global temperatures have risen already 1 degree in the last 100 years, and the projections are that the global temperatures will rise between 2 and 6 degrees in the next 100 years. And this is really scary. And the cause of this, of course, comes from our own evolutionary biology. There are two causes. The first is there are too many of us. Remember, hunter-gatherers figured out how to have higher interbirth intervals than chimpanzees, but farmers went, doubled that and more, right? So farmers can have 1 to 2 offspring every year. And we've all these inventions like the toilet and medicine and new food technologies have enabled populations to skyrocket. So there are so many of us. There are going to be 8 billion of us on the planet by the year 2025. There are a lot of us, and we use a lot of energy. Remember, we are gas guzzlers, right? If we lived in the habitats we evolved in, which is normal, right? We wouldn't have to do what we do in the buildings here at Harvard, which is heat them all the time, right? We use a lot of energy heating buildings. And we also use a lot of energy moving about. And I think this is part of being a human being, right? Hunter-gatherers walk 12 to 15 kilometers a day in many habitats. We have that same desire to move about, except we do it in cars. The typical human in the US drives 52 minutes a day. That's 32 miles. Pumping carbon dioxide into the atmosphere. When you have billions of people driving 52 minutes a day, it's not a surprise that we're in trouble. Our food, for example, has become technological. It takes 10 kilocalories of energy to grow 1 kilocalorie of edible food. And it actually accounts for 10% of the fuel use in the United States. So this has led to what I call disevolution. I'm not happy about the term. I haven't come up with a better term. And you can, if you don't like the term, come tell me something better. But it's a simple idea. It's that we're in a positive feedback loop, and a special kind of positive feedback loop, in which the cultural buffering mechanisms that we have are addressing the symptoms of the problems that we have, not their root causes. And so it keeps the system going. It makes it worse and worse and worse. So the problem is getting worse, not better. So let me explain in another way. When you have a biological challenge, such as some mutation or some problem, natural selection, the way natural selection operates is it would filter out the problem. Either it would be removed from the gene pool, or some feature maybe that made us better at dealing with the problem might get selected positively, and we'd solve the problem that way. But with cultural buffering, we invent a solution, and we enable the problem to persist, and in fact to get worse. Let me give you a non-threatening example first before I scare the pants off you. So the non-threatening example is bad vision. Now there's a lot of debate as to what causes bad vision, but basically it's caused by an eyeball that's too long, right? Myopia, right? And it turns out there's some interesting theories. One theory, I'm not saying it's correct, it's just a theory, is that higher levels of starch in the diet raise the levels of IGF-1 production. It's a growth factor in the eye, and it causes the eye to get too long. And in fact, you can give dogs really starchy diets, and they develop myopia too. Now, if myopia were a problem in the past, which I imagine it would be, if you were being, say, chased by a woolly rhino, you'd be selected very rapidly against, right? So natural selection would have filtered out the problem. In fact, we know from ethnographic studies of hunter-gatherers that vision problems were very rare in the past in pre-industrial societies. You go to Inuit societies from a long time ago, and nobody needed glasses. Now they all need glasses just like us. So what we do is we have cultural buffering. Eyeglasses or now LASIK surgery and contact lenses. And that enables the problem to persist. And with eyes, well, that's not such a big deal. But some of these problems are much bigger deals. So we have all these physiological drawbacks of civilization, and we are devoting incredible amounts of money and energy in our society to treating the symptoms of those problems. For obesity, we've got how many diets are there out there? Then you can buy books to tell you how to basically do what all diets are, which is basically exercise more and eat less, right? Or we can have stomach reduction, or insulin injections for diabetes, and drugs for osteoporosis because we don't exercise very much, and therefore we don't build up much bone mass in our skeletons, and chemotherapy to address cancers which are on the rise, largely because of higher levels of hormone, and orthotics for sorry, I'm obsessed by feet. I can't help mentioning orthotics. And again, this is creating disevolution. I don't know how many of you have seen the movie WALL-E. It's a great film. If you haven't seen it, I think you should see it. Not only is it charming, but it's also scarily believable. It's about a world in the future where people have abandoned the Earth and they're living like big fat slobs in a spaceship in Earth, and they float around and they don't really do anything, and it's all rather too close to home, right? And what's going on? Well, we have this horrible lifestyle. We drive everywhere. We take elevators instead of the stairs, and we eat Wonder Bread, and we do this sort of stuff, and we get fat, right? And we get obesity, and we get diabetes, and so we have liposuction, and we take Fosamax, and we take all kinds of drugs, which allows us to perpetuate our lousy lifestyle in which we take elevators and eat Wonder Bread, and etc. You can see how it works. Can we sustain this evolution? Well, maybe we can. But should we? There are some real serious costs. One of them is that it clearly reduces the quality of life. Old people who have diabetes and osteoporosis and all those other metabolic diseases have a reduced quality of life than people who don't have those diseases. We spend a fortune. I don't even know if we can calculate how much money we spend in our society combating these diseases. And of course, it's too scary to even think about global warming and the ecological disasters that we're promoting because of our lifestyle. Does evolutionary logic propose any solutions? Well, there are two. One I don't like, and this is it. One I don't like is that we keep the positive feedback loop going. This is really known as the Red Queen phenomenon, right? Remember the Red Queen from Alice in the Looking Glass who tells Alice, now here you see it takes all the running you can do to keep in the same place. And that's really what we're doing here. If we keep up with this and we keep inventing new drugs to combat diabetes so we can keep getting fatter, etc., we'll keep the system going, and maybe we'll be just fine at it. And that's really where our society is going now. We're throwing billions at NIH to keep this system going, right? That's really what we're doing. Now, I'm not saying we shouldn't throw billions at NIH. I'm all in favor, actually, of throwing billions at NIH. But I think we have to do more than just that. We also have to become our own filter. We have to take the place of what natural selection would otherwise do to promote better ways of living. In other words, we have to address the causes of disevolution using culture, right? And actually, we already do that. It's not that controversial an idea. For example, we tend to be particularly sensitive and concerned about the fitness of we do a lot to protect our children. So we know that smoking's bad, so we don't let children smoke, or drink beer for that matter. We don't let children, adolescents, drink. We know that automobiles kill a lot of people, but we make children ride in these special seats that are supposed to protect them in car accidents. That's all logical, right? We all accept that as part of the world we live in and what we should be doing. But that's just the tip of the iceberg. Why don't we do more, right? We know that fast food kills. We shouldn't be allowed to call it food. We should call it something else, right? It's lethal. It's killing children, right? It's not killing children, but it's disabling them. Our world is filled with escalators. My family can tell you my blood pressure goes up every time I go there, and there are these moving sidewalks and escalators. I'm always hounding the students in my classes not to take the elevator when they go to the 5th floor of the Peabody. We're constantly using these methods of saving energy because we're lazy, but they're not good for us, and they're not good for the environment. We should tax gas more, and we should certainly ban corn-fed beef. I don't know how many of you know about corn-fed beef, but cows evolved as ruminants, right? They have 4-chambered stomachs. They evolved to eat highly diets with lots of cellulose. And when we feed them corn, which is very starchy, the cows get sick. They have a constant state of diarrhea, right? So we have to feed them antibiotics all the time. And there are feedlots out there in the Midwest with cows, they're larger than Boston, filled with cows with diarrhea, right? Creating very fatty beef, destroying the environment, producing lots of methane, and we eat the stuff. It's disgusting. We should outlaw it. It's not good for our health. It's making us fat, and it's making us sick, and it's immoral. But we don't. Is there any legislation to stop corn-fed beef? It's actually very serious. Now, some people would say that I'm espousing radical ideas, but I don't think they're radical. We do this all the time. It's just a question of degree. It's a question of how alarmed we have to get before we act. We make children learn. Why don't we make them exercise? You know, most schools have abandoned physical education, more or less. And when we do have exercise, a lot of it is basically useless, right? I have nothing against baseball and football, but they're not endurance sports. They don't promote long-term health, unlike sports such as soccer or running, which are better for people, right? So, you know, this is something that we don't do in our society. Even here at Harvard, I think we need to look at what we're doing. I mean, Harvard has one of the great medical schools in the world, maybe the greatest in the world, and we do a lot of fantastic research on curing various kinds of diseases, and that's a good thing. But many of us here at Harvard probably don't get enough exercise. How many of you in this room exercise vigorously more than 2 times a week? Right, you're like Harvard undergraduates. I see about half the room raise its hand. That's true also of our undergraduates. What kind of education are we giving them when we don't encourage them to exercise as well? Because we know the path they're heading on. And unless we come up with some better solutions to diabetes and heart disease and osteoporosis, they're going to be in the same trouble that we're going to be in. So where does this start? I think we need to have more education about how our bodies work and how our bodies evolved, because it's not just interesting, it's actually fundamentally important for our future. You can be a biology major at Harvard now and not actually have to take physiology. I'm concerned about that. And we need to do more to promote fitness. Why not have a run and try to get everybody here at Harvard to run a marathon? That's something we're working on, and I hope to see you along the Charles on October 25th in the fall. I think we should ban corn-fed beef here at Harvard. We should. I don't want to see anybody I know using an elevator unless you have broken your leg. And why don't we turn Harvard Yard into a victory garden? And the list could go on. The list could go on. But my point is that if you think about our problems from an evolutionary perspective, think about their root causes, not their proximate causes, you end up thinking about them in a different way. And I think that's the genius of Darwin. Because Darwin, again, didn't know about genes. He didn't know about transcription factors. He didn't know about all the little nitty-gritty about how cells work and how biology works at the microscopic level. But he was able to see the big picture and to put how it all goes together. And how we evolved and the way in which our bodies came to be the way they are is not only important for understanding ourselves, but it's also, I think, important for understanding our future. So we need to think more like Darwin, and we have to act more like hunter-gatherers. So thank you very much.